Neutralization is the word for today. Before we talk about neutralization, we need to talk again about what makes something an acid, a base, or neutral. And to do that, we're going to look at a molecular view of three different beakers, beaker A, B, and C. So what we're doing here is we're zooming in and looking at the individual molecules and kind of doing a head count there. So for this first beaker, beaker A, we can see in all of these little view, and over here is the key. So the little dots, those represent H's, so a single dot would be H+. The big ones are oxygens, so a big dot and a little one is oxygen and hydrogen, a hydroxide. And then two H's and an O is water, of course. So first thing we want to do is a head count. If we take a look at this first beaker, beaker A, the concentration of H+, and let's just count them. There is 1, 2, 3 H pluses. The concentration of hydroxides, there is 1 hydroxide. And the concentration of water, there is 3 waters. Okay, so is this acid, base, or neutral? So water doesn't really have an indication on what it is, but the H pluses and the OH minuses do. So in this case, there is more H pluses than there is OH minus. And if you have a greater concentration of H plus than you do of hydroxides, that means the solution is acidic. So beaker A is an acidic solution. We know that because there's more H pluses than there is OH minuses. There's a greater concentration of protons than there is hydroxides. Remember that something that's acidic doesn't have only H pluses, it just has more H pluses. So even acidic things, all acidic things are going to have hydroxides in them as well as H pluses. It's about the imbalance. Let's take a look at beaker B then. So the head count of H pluses in beaker B is 1. The head count of hydroxides in beaker B is 3. And the head count of waters is 4. So in this case, if we once again compare the H pluses and the OH minuses, we can see that there is more OH minuses than there is H pluses, and that means this solution is basic. Okay, so we have more hydroxides, that means it's basic, and we still have protons in there, we still have the H pluses, we just have less of them than we do the hydroxides. And last but not least, our H pluses in beaker C, we have 1 of those. Our hydroxides in beaker C, we have 1 of those. And our waters, why, we have 4 of those. So in this case, if we compare H pluses to OH minuses, we see that they're equal. So that means that this solution is neutral. So it's all about the imbalance or the equality. So if you have an equal number of H pluses and OH minuses, that is a neutral solution. That's going to be right in the middle with a pH of 7. If you have more H pluses than OH minuses, that's going to be basic with a pH above 7. And if you have more H pluses than you do hydroxides, that's going to be acidic, which is a pH below 7. So beaker A is acidic, but we can make it neutral by neutralizing it. And by neutralizing it, that means we need to have it so that H plus concentration equals the OH minus concentration. If those two are equal, that means it will be a neutral solution. So let's do this. Let's imagine that we take beaker A and we pour it into beaker B. Let's do a head count now. So those two are combined. They're all mixed together. We would have, in that case, we would have 3 H pluses from beaker A and the 1 from beaker B. That makes 4 H pluses. And the hydroxides, we would have 1 from beaker A and 3 in beaker B. That makes 4 hydroxides. So by combining those two together, we now have a concentration of H plus that is equal to the concentration of hydroxide. What does that mean, ladies and gentlemen? It means that this solution is now neutral. So neutralization reactions involve combining an acid with a base, and among other things, they generate H pluses and OH minuses, forming water, and then water creates a neutral substance. So as long as you have an equal number of H pluses and OH minuses, you will neutralize that solution. Or you can just adjust the pH. You know, if we were to add a little bit of beaker A to beaker B, a few of those H pluses, we might make the solution in beaker B a little more acidic, so make the pH go down a little. we could pour a little bit of beaker B into beaker A and then raise the pH of beaker A just slightly to whatever pH we want to adjust it to. Alright, let's take a look at an acid and a base reaction. So this right here is hydrofluoric acid. That's an acid, obviously, because it's got the H in front. And this right here is a base. It's potassium hydroxide. It's got that OH minus in it. So the good news is neutralization reactions are nothing more than another double displacement reaction. Just a partner swap going down, and that's going to give us water and a salt. So let's take a look at this first one. And since both things are aqueous, acids and bases are always aqueous, that means really it's not HF, it's H plus and F minus. And KOH isn't really KOH, it's K plus and OH minus. So when these dudes undergo a partner swap, your H plus is going to go with your OH minus, and your K plus is going to go with your F minus. What that's going to give us then, H plus, OH minus, that makes 2 hydrogens, 1 oxygen, which would be nothing other than water, H2O. And when those two guys combine, potassium and fluorine, you would get KF. So now, when those combine, KF is going to be aqueous. We know that from our solubility rules, and H2O is a pure liquid. So if we wanted to get fancy here and write the net ionic equation, well, K plus stayed K plus, F minus stayed F minus, so it didn't really change. So really, the net ionic equation for a neutralization reaction is H plus OH minus yields water. That's really what's going down. That's what's changing, because what makes it acidic is the H pluses, what makes it basic are the OH minuses. And so when you combine those two, you create neutral water. So the only real reaction that's going on here is the acid being neutralized by the base, or vice versa, to create water. But in the full equation, we would write this as KF plus H2O, and that would be aqueous, and that would be a pure liquid. So if we give some names to these different products, over here, the two things that are always created by an acid-base reaction, by a neutralization reaction, two things always created. One is water, and water is always H2O. So you know that a product, when you see an acid-base reaction, has to be water. The other thing that's created is what we call a salt. So it's not the salt, okay, NaCl, sodium chloride, table salt. Salts are ionic compounds that are created by an acid-base reaction. Say that again in case you're writing that down, which you should be. A salt is an ionic compound created from an acid-base reaction. And so you're always going to generate water and then a salt. And the salt's just going to be the cation from the base and the anion from the acid together with their charges balanced. Alright, here's another one. Sulfuric acid reacting with sodium hydroxide. So what two products is this going to create? Alright, close your eyes, don't look at it, don't cheat, don't even need to know what the different anions and cations are. We know that one of the products has got to be H2O. Now we can go and look at the different things and figure out what the salt is going to be. We know H2O is always H2O. So in this case we have sodium as our cation from the base, that's Na+. And we have SO4 as our anion from the acid. That's SO4 2-. So when we combine those two, following the old-fashioned rules, we would need 2 and SO4. So that means the salt in this case would be Na2SO4. So as always, we have generated water and a salt. And don't forget about balancing the molecules as well. So we would have 2 of those to balance out the sodiums, and then to balance out the waters, we would need 2 right there. So make sure you're balancing charges and balancing for atoms. Alright, here's a final practice problem. So go ahead and try this one on your own. Pause the video and then resume it to check your answer afterwards. Alright, so you should of course gotten water as one of the products, and then when we make our salt, it's going to be Mg plus and ClO4 perchlorate, and so that's going to be Mg2 plus ClO4 minus, and that yields for us the salt of Mg, in parentheses ClO4, and there's 2 of those. And then to balance out the atoms as well, we would need 2 perchloric acids, and we'd be generating 2 waters. Alright, so that's a neutralization reaction. It's just a fancy double displacement reaction. You generate a salt and you generate water every time. Something I want you guys to know, write this down in your notes, circle it so you do not forget it. Neutralization reactions do not always yield neutral solutions. They don't, because you have to mix evenly in order to get a neutral reaction or neutral solution. So for example, if we just combined 1 to 1 here, if we put 1 mole of the HClO4, your perchloric acid, and 1 mole of your MgOH2, that wouldn't be enough to neutralize it, because you required 2 perchloric acids for every 1 of those. And so that means this solution, while it would be slightly more acidic, so it would raise the pH or lower the pH a little bit, it would not neutralize it. In order to neutralize it, you would need 2 moles of HClO4. Okay, so not all neutralization reactions give you neutral. They have to be mixed perfectly evenly in order to generate a neutral solution. Okay, other than that, it's all pretty simple.